Hi, this is the Robotic Pole Inspection Collar project presented by Group 7. To summarize our project, uh, wooden utility poles are used by most power companies across the nation. They can't be replaced for certain logistical reasons, so it's important to monitor the health of them as they are prone to wood rot and other issues. To protect the safety of the linemen, we want to construct this robot so that it can first do a preliminary examination so that the lineman can make a decision if they feel safe climbing the pole or not. So our solution will consist of a climbing system, hammer test, a rechargeable battery, and a user interface. These will all be controlled by a microcontroller, and our final design will be able to satisfy the following conditions: ascend and descend the pole safely with no harm to the lineman or to the collar itself, perform and send results of the hammer test to the user, wherein it will measure the structural integrity of the pole so that the lineman knows if they can climb it or not, and the entire system will be controlled by a mobile app, which is also where the user will receive the data from the test results. So a typical use case for this would be the lineman attaches the collar to the pole, presses a button, and establishes initial tension. The user then opens the mobile app and connects via Bluetooth to the collar. He will then control the collar to go to the desired height he wishes to test. He will then initiate a hammer test at that point. Once the test is completed, the individual strike results as well as the overall results will be sent back to the mobile app for him to review. And once he's done, he'll lower the collar to a level that he can reach and then disengage the tension from the collar and then remove from the pole. Here's a basic system overview for our collar. As you can see, every subsystem interacts with the microprocessor, but there is a little to no interaction between individual subsystems. That'll all be handled by the microprocessor. So the 5 systems for our robotic pole inspection collar will consist of a climbing system, hammer test, a user interface or mobile app, a microprocessor, and a rechargeable battery. The user will interact and control the collar solely through the mobile app, where they will send commands and receive test results. The climbing system will allow the collar to safely ascend and descend the pole. The hammer test will perform the structural integrity test on the pole and present the results to the user. Once they're processed by the microcontroller, the test results are sent back to the user. And the system will be powered using two 20-volt power drill batteries that are usually carried by FPL linemen to increase utility.
3D collar design. For the 3D collar design, we had to use dimensions from the largest pole diameter to the smallest pole diameter, basically going from 13 inches to 6 inches diameter. And then using that, we used the distance between the actuator base and the dual shafted motor mounting area to determine the offset from how far the collar has to be and how far the collar's inner ring has to be offset from the actual pole to have enough space when going up the largest class pole to understand how far we should space our inner ring from the actual pole body. Afterwards, we had to break down the collar body into enough unassembled components to fit an available print bed. We had to figure out the locations of the mounting areas for the climbing subsystem, because otherwise the force applied from the tensioning mechanism might actually cause the pole body to break down. Then we would have to use the rough estimate of other components inside to make the cavities inside the collar. The main challenges with the 3D design portion was the management of force created from the tensioning components of the climbing subsystem, a huge range difference between different classes of poles, and a less obvious issue but still very pertinent was the assembly of the collar after printing, as the collar is made in sections and the correct assembly is essential for its structure. For implementation, in the research aspect, me and my group collaborated by looking through many different patents, and based on all these patents we had a lot of inspiration of how we should make the design. One inspiration was the use of dual shafted motors that automatically stop after not receiving any power. Another one was the use of a traditional circular collar. For component creation, I basically implemented several parts, including 4 different parts of the collar body to fit the printer bed size, copies of the actuator part, parts of the dual shaft motor, and assembly of all the components together, so that we have a final representation and a print for the collar.
For the climbing subsystem, we plan to implement it using the following components: a high torque dual shaft DC motor, 4 of those to allow the collar to climb the pole, 8 rubber wheels, 2 to each motor, used to provide traction on the pole for the collar, 4 linear actuators, 1 for each motor, used to provide tensioning on the collar, 4 force sensors, 1 for each linear actuator, used to provide feedback to the microcontroller to ensure tension remains in an optimal range, and 4 motor driver boards, 1 for each DC motor, to allow the microcontroller to control said motors. So here's the state diagram for the climbing subsystem. It'll start at an idle spot. Once the user press one of the movements up or down, it'll check tension. If tension is bad, it will tension before movement is allowed. Once tension is established to be good, it'll either move up or down. Once the movement button is unpressed by the user, the system will move back to an idle state and thus repeat. So this subsystem will be directly controlled by the microcontroller. It'll receive commands via the mobile app, which will then be processed by the microcontroller and sent to the motors as needed. There'll be a feedback loop between the microcontroller and the linear actuators to ensure that tension stays within an acceptable range at all times so that the collar can both climb and is in non-danger of falling off the pole. This subsystem, along with the other ones, will be powered by the 2 rechargeable 20-volt drill batteries and will make use of buck converters to maintain the 12 volts needed to power the DC motors. The challenges we have to overcome for this are ensuring that the force sensors are receiving proper readings. If they're too low or too high for what they should be reading, the collar can fall off the pole or be unable to climb the pole. For the linear actuators themselves, we need to ensure that they are stable enough that fully extended for the large range of poles we need to accommodate, that they don't crack or get damaged under the stress they'll be under providing the tensioning. And then finally, the DC motors will need to have sufficient torque to carry the full collar load. Unfortunately, due to a lack of linear actuators from the parts lab, we haven't been able to begin implementing this subsystem as that is a first initial step. We did do a lot of research due to our lack of mechanical engineering knowledge that we ended up finding was required for this. So we did research into the torque required, thus we got the high torque motors. And then we also confirmed via a published paper by Lee that using linear actuators is an established and very reliable system to use for tensioning, especially when a large range of poles would need to be covered. We also found suitable buck converters for ensuring that we can step down the voltage to the required 12 for the DC motors.
Hello, I'm John Carlos Gomez, and I'm responsible for the hammer test subsystem. The goal of this subsystem is to replicate the standard method of testing utility poles, which is the hammer test. The issue with the current hammer test method is that it requires a lot of personal experience, good hearing, and ability to distinguish rebounds for the technician, making it a very subjective method of testing. This means that newer technicians or less experienced technicians have a higher chance of human error, which could put them at risk for an injury or death. Our goal is to conduct strikes with the mass attached to a servo motor, which is attached to a linear actuator on top of a cart to replicate the hammer test. This cart is powered by a DC motor and runs on top of a track around the whole collar. 12 strikes will be conducted, 1 strike at every 30 degrees. Strikes will be picked up by a microphone under the collar. Our goal is to standardize the hammer test method so it becomes a reliable and safe way of testing wooden poles. This subsystem is made up of a cart body and wheels, a mini DC motor which is used to move the cart around the track, a 2-piece metal track which is placed on the top portion of the collar, a microphone which is used to extract sound of each strike for the microcontroller to process it, a mini linear actuator which is used to adjust the distance needed so the servo motor can strike the pole, a motor driver board to control a DC motor with the microcontroller, a servo motor to move a large surface area mass for striking the pole. An ultrasonic sensor is used to detect how far the servo motor is from the pole. This is the state diagram. This subsystem interacts with the user interface subsystem. Once the user gives an input, the cart moves 30 degrees, strikes the hammer, waits and listens, and processes it. Then it checks if 360 degrees have been met. If it has not been met, it goes back 30 degrees and keeps going over this little cycle until it comes back to the starting point, which then at that time the microcontroller will process and display the results on the mobile app, and the system goes back to idle. Challenges. What are some challenges? What are some challenges? Well, getting both sections of the tracks to line up perfectly to prevent any issues with the cart is a challenge. Our solution for this is to create a puzzle-shaped connection for both collar sections and using a holding screw to line both tracks up perfectly. Another challenge is determining a range for undefined spots, as some strikes can be questionable. You can't determine if they're good or bad. Another challenge is determining adequate striking distance and establishing a constant force on each strike, as varying pole sizes can influence how far the linear actuator goes, and this could lead to some discrepancies. Another challenge is determining the exact time window needed for the microphone to record each strike, as the length of time of the recording can influence certain values like the RMS value and the crest factor. For implementation, so far, we have extracted audio of good and bad strikes from a wooden utility pole at FAU. We used the microphone of a Google Pixel 4a. We replicated the hammer test with a hammer. We used MATLAB and Audacity to discover trends that distinguish good and bad strikes. We used a MATLAB file created by Hristo Zhirmanov that gives us various forms of sound analysis. Viable options of determining a good or bad strike was determined. We can define good and bad strike ranges based off of the crest factor of the signal. We will also set up an undefined range in between the known ranges due to some strikes sounding questionable. We also propose using machine learning to analyze images of the spectrogram and corellogram. We plan to meet with Choi, our sponsor, on August 4th to have alignment and show us a proper hammer test in person, and also to extract more audio samples. This is what a good strike looks like. On the corellogram, we can see it has a high amplitude, a clear shape, a wide kind of diamond star shape, and on the right hand spectrogram we can see that the yellowness is less pronounced and narrow. This is a bad strike. Here we can see some fuzziness on the corellogram. The amplitude is much less, it's distorted, and on the right hand spectrogram we can see more yellow and a wider yellow range. The crest factor is taking the peak amplitude of the waveform and dividing it by the RMS value of the waveform. Through trial and error with 30 plus samples, we determined the following ranges. Good ranges fall below 18 decibels, bad ranges fall above 19 decibels. Undefined range, we believe it to be between 18 to 19 decibels. The RMS value, and thus the crest factor, is influenced by less length of time of recording. We tested one strike sound with 3 different lengths of time by adding silence and audacity. However, the length of time does not impact spectrogram and corellogram output, it just scales it. So it may look smaller or bigger, but it's the same. I'm also responsible for the rechargeable battery subsystem. Our goal with this subsystem is a rechargeable battery system that will last at least 1 hour and power all collar components. Ideally, we want to use the 20-volt drill batteries, which are easily available to linemen, like this one presented. Components. We want to use 2 20-volt batteries, as this will ensure that there's sufficient power and also improve the battery life of the collar. 2 batteries will allow the collar to be balanced as well. We want to use a power wheels adapter for 20-volt batteries, which is used to make positive and negative terminals of the battery easily accessible. and we want to use DC to DC buck converters that are adjustable so we can step down the battery voltage to the appropriate voltage needed for each component, like using 2 of these converters for motors and actuators at 12 volts and using 1 of these converters at 5 volts for the microcontroller and sensors. This is the state diagram for the battery subsystem. It basically constantly changes between idle, charging, and discharging. What are some challenges for the battery subsystem? Well, ensuring a battery lasts at least an hour. All components receive the correct voltage and current. The system is properly and safely wired to prevent any hazards. Wire management. Determining wire length for moving parts like the linear actuator to prevent excessive wire from leading to complications in the system. Figuring out how to display the remaining battery health of the collar to the mobile application. Rechargeable batteries tend to be harder to monitor compared to single-use ones.
Alright, here we have the state diagram of the user interface subsystem. It starts out waiting for user input, and upon receiving input, it sends it to the server. It'll process the input and then transmit it to the microprocessor. And then the microprocessor will execute another subsystem, such as the climbing or hammer test subsystem, and then it goes back to waiting for user input. In order to control the robotic collar remotely, we're going to create an Android app. The application will contain the following things. It'll have controls to move the device up, down, perform a hammer test, and stop. It'll display the current battery level, and it'll allow you to view the results of the hammer test. The app will communicate with the microcontroller via Bluetooth to send instructions and receive information. Challenges with the mobile app and user interface. One is sending commands to the device with Bluetooth. So we have to figure out how to send different signals to the microcontroller and have it read those signals and perform a different task depending on what it receives. Another is tracking, displaying the battery level. We have to figure out how to detect the battery level in the rechargeable battery and then transmit that back to the app to be displayed. And another is disabling controls until the device is ready to receive the next instruction. So if the collar is performing a hammer test, you wouldn't want to overload it with more instructions such as climbing up or down. You'd want the hammer test to finish, and then the collar can send a signal back to the app noting that it's ready to receive the next instruction. For the implementation of the UI design, we created a mock-up of the Android app user interface. So we tried to keep everything on one screen for simplicity, but we may decide to make a second page to display the hammer test results in the final product in order to reduce clutter. We kept the controls simple with 4 buttons, one to go up, down, perform a hammer test, and stop. We also display the analysis of each individual strike on the pole, and the overall health of the pole is given at the end to determine if a pole is a pass or fail. If a strike falls in the undetermined range, then UND is displayed, and the battery health of the collar is displayed in the top right corner. For the microcontroller functionality, the microcontroller will act as the central unit for the collar, and all inputs and outputs will pass through it. It'll receive feedback from the force sensors of the tensioning system and use that information to decide if adjustments are needed and enact them. It'll receive the recorded sound wave from the hammer test system, and then process the test results on board and pass the results to the user via mobile app. And it'll connect to the user's mobile app via a Bluetooth connection. Bluetooth has lower power consumption than other methods and has the required range the collar will need to operate and send data. Some challenges with the microcontroller. One is ensuring the microcontroller sends and receives data from the other subsystems in a reasonable time and fully intact. Too slow, and the climbing subsystem's DC motors could come out of sync, preventing the caller from climbing. Corrupted data can result in errors for the feedback control needed on the tensioning system, causing the caller to fall from the utility pole. Proper analog to digital conversion for the sound signal processing for the hammer test. If a microcontroller that doesn't read analog inputs is used, then we need to include an ADC with reasonable resolution for our purposes. One example of this is the Raspberry Pi, which does not have an analog to digital converter built in, so for that we would need to use a separate ADC module. Using a database and a web app would be an extra feature if time permits. A web application would allow a wider variety of devices to be used. So instead of just Android devices, someone with an iOS device or a PC or anything else that can connect to the internet would be able to access the app. A database would allow hammer test results to be saved and stored for future use, so the test results can be retrieved from the database and viewed in the application. A database could also be implemented as part of the Android application instead of the web application if we don't have time to do a web app. And using web application to communicate with the caller has disadvantages such as latency and availability of internet in the field. This is one of the reasons why we chose to use Bluetooth over a web app. Someone might be working on a pole and they might not have internet available where they are, so they would have issues being able to communicate with the server and therefore to the device.
Coming to the outline of the plan. In stage 1, we're going to design, print, test the caller, then we're going to obtain parts, audio processing, mobile apps. Moving on to stage 2, where we're going to create the climbing system, create the hammer subsystem, create the rechargeable battery subsystem. Moving on to stage 3, where we're going to combine all the subsystems, do any troubleshooting that may occur, and then we might have a database to interact with our web app, and we might have to refine the caller system and its 3D design if any issues have come up. This is how we want to schedule the project, right? For the caller design, I'm overseeing it, and my deadline is 8/23, and the contingency, there really isn't any because I basically am the only one in charge of it at the moment, and without a good design of the caller, we won't really be able to go work through this. Moving on to the signal processing, it's going to be a team effort with John Carlos and Kevin, and and a couple other people, but they're mostly working on the data portions of it. And they're going to be working through basically classifying it if it's good and bad from the Boca Center, and later on FPO will help us out with a better comparison of what bad and good signal is. We're going to obtain parts. We have to have that done by 9/6/21, and our contingency is the shipping times and part availability. The Bluetooth module is set up. As we originally thought it was going to be a separate module, but we're going to be using a Raspberry Pi. It's not as necessary, but we might have to do it later on. The rail system, we're going to be using tools at FAU to create a custom rail out of sheet metal and laser cut if it is necessary for the actuator to sit on top of. The climbing subsystem, we're going to be using a tensioning system with mandrel screws or linear actuators that Kevin's in charge of. And the contingency is collar design. I'll help out Kevin if he needs any help with it. Then we need to create a cart with a hammer. This is basically what sits on top of the rail system. It's going to create a cart for DC motor that runs on the track. The cart will hold a linear actuator or a mandrel screw to strike the pole. And a contingency plan for that is rail design and collar design. Moving on to the next part of the project schedule, the rechargeable battery. John Carlos, our electrical engineering major, will be setting up a rechargeable system that powers up all the components. Moving on to the fully functional mobile app by Ryan, our computer engineer. He's going to be designing a mobile app that allows users to interact with the collar. The app will allow the user to move the collar up and down and conduct the hammer test. For wiring the collar, our two electrical engineering majors, John Carlos and Kevin, will be handling that, and our contingency for that is a climbing subsystem, and the hammer test subsystem must be also completed. The functionality of the sensors and microcontrollers. We have to ensure that all subsystems are operating correctly, and Jose will be in charge of that. And the wiring has to be complete before that. For the final unit and the final product, the whole team will be in charge of this. And the contingency is everything else before this has to be done. And if we have time after, we're going to be working on a database to work with the web app, as we would want to do something a little bit more than just an Android app to have it work on iPhones as well. Going through the general task for all of us, we all decided to basically work together to collect audio samples. Me and Giancarlos are going to be working on a Rails system together, designing it. Web application, since I'm CS and Jose is CS, Ryan is CE, we might work on the web app together if it's possible. If not, we'll just leave it to the Android app. And wiring the collar, we're going to be working on that collectively, as we all have a part in that. For me, I'm basically doing the tasks in SolidWorks. That's going to go through creating different couple components and then putting them together as assembly. We can use that to print out the main collar bed and have a model to work off how everything will be mounted and used together. And afterwards, I'm going to be doing Bluetooth module interaction, which is basically just how the Bluetooth module on the Raspberry Pi will be interacting with our phone app, the Android SDK. For Kevin, he's going to be working mostly the pole climbing subsystem and an tensioning component of that pole climbing subsystem. Giancarlo is going to be covering the hammer plus the microphone portion of it and the rechargeable battery subsystem. Ryan is going to be covering over the app design. He's going to implement Bluetooth connectivity, remote power control, send commands from the app, display battery life, and display the hammer test results. Jose is going to be covering our microcontroller functionality for all the sensors and basically working with all the interfacing that we need to have. And he might be doing the database using Amazon Web Service or some database for our web app that's possible in the future. And that concludes our project. Here's our team.